Hello everybody, this is me Khalid Mehraj Malik over again with a new video today. We are studying magnetism and we have already gone through one lecture of magnetism portion in which we have been studying about MMF, reluctance etc. and flux density, magnetic field strength etc. The basic definitions of magnetism. Okay, in this today's lecture we shall be studying about air gaps and magnetization curve etc. Okay, starting with it. Air gap. Air gap. To depict it, I shall make a diagram. I shall make two diagrams in fact. Let us have an iron core like this. Let this be an iron core. Some C-type block of iron. Okay. If we wind a coil with N turns upon it, passing a current through it, current I, this will create a flux in it. This will create a flux in it. The path of the flux will be something like this. Okay. In this system we see we have this C-type iron core. Here there is iron, then there is an air gap. The discontinued iron, that is called air gap. Then over again iron, then air gap, then again iron. So this is a series air gap. This one is a series air gap. This portion. The iron has mean length Li. Say, mean length of iron, mean length of iron, Li. Okay. Mean length of air gap. Mean length of air gap Lg. So the permeability of this iron block or iron frame, whatever you call it, is different to that of iron. Permeability of iron part is equal to mu. Permeability of air gap is equal to mu naught, that is fixed 4 pi into 10 power minus 7 is the value Henry per meter for mu naught. Okay. Permeability of iron part, it is an intrinsic property of this iron. It is an inherent property of this this solid object, this iron core, that it has some fixed permeability mu. Relative permeability mu r applies to both those parts, this iron part as well as this air gap. and mu r is relative permeability and it depends upon certain factors we shall be studying further. Then we shall see on what factors does mu r depend. Okay, what do we do in series air gap? We find now here there is a current that is flowing through this coil that is wound over to the iron core. Current creates a flux in this. Current creates a flux in this. The value of flux will be phi. The value of flux will be phi. Okay. What will that phi do? What will that flux do? That will create ampere turns or mmf. We have studied this in our previous lecture. Okay. So the mmf for this iron part shall be worked out separate, and the mmf for this air gap shall be worked out separately. Then both of those mmfs will be added and we will get the total mmf induced in this air gap plus iron portion. Okay. Coming upon another type of air gap now. Let us have an iron block of this type. Let us have an iron block of this type. Say if a coil is wound to the central part of this iron frame with current I, this will induce a flux. This will induce a flux in this iron frame, and the path of the flux will be something like, say, like this. There will be in fact two paths. Here we see two paths of the flux will be created. So this air gap will be called a parallel air gap. This air gap will be called a parallel air gap. Okay. The paths will here bifurcate like this. Paths of what? Paths of flux. One path will be this. Another path will be this one. Another path of flux will be this one. It is not necessary that both those halves of this iron frame, those are equal. They can be this central portion can be inclined to one also, and those two parts may or may not be equal. So the fluxes induced in those two paths or those two parts of this iron frame, they may or may not be equal. Say flux induced in this one is phi 1. Flux induced in this two is this second one is phi 2. Okay. The current is I. So here length of air gap Lg over again, mean length of this iron frame Li again, Li over again. Permeability of iron part, permeability of this iron part over again mu. Permeability of iron air gap mu naught, that is fixed 4 pi into 10 power minus 7 Henry per meter. Relative permeability mu r, that will be variable, that is not always constant. That relative permeability varies with certain factors, so called relative permeability. Okay. We have flux phi is equal to, now first of all let us see total, see mmf for, let us call this portion A, B, C, D, E and F. Point A where the fluxes meet, point B where the fluxes meet, and point C, point D, point E and point F at the corners. Okay. mmf are ampere turns. mmf are otherwise called as ampere turns. mmf are path AB. Path AB constitutes this ear gap, some part of iron as well, but mainly ear gap. mmf for path AB, that is air gap path, plus mmf for path BCDA. This will be equal to mmf for path over again what is common between those two, the path AB path is common to both of those two sides of this frame. mmf for path AB plus mmf for path which path? A B F E. Here the fluxes will bifurcate and here they will over again meet. So mmfs for path central path plus one side is equal to mmf of central path plus another side. They will be equal. Here in this case, if this is symmetrical, this is just same on the both the sides. Okay. Here in this case, flux phi, that is ampere turns or mmf upon L upon mu or mu naught A. Suppose the cross sectional area, this iron part will have some area, this iron part will have certain area. Okay, this one is that area. So the flux is this, or ampere turns will equal to phi cross, what is the length of this total part? Li plus Lg, length of iron part plus length of ear gap divided by, what is mu r here? Mu r is the relative permeability, mu r, and what is mu naught? If suppose we have to find this for this air gap only, so for air gap it will be Lg, divided by mu r will be as such, and for ear gap mu naught will apply. Okay, but in case this one 80, this one ampere turns or mmf will be that of this ear gap, but so say this is for ear gap. But if the same ampere turns or mmf is to be found for this iron part, say if we have to find it for iron part, then what will happen? The flux phi will be the same. Here, in spite of G, it will come I, and for iron part, permeability is mu, so mu naught, erasing naught, so mu will be there. So both the ampere turns, I have omitted it. You would have written it upon your notebook. Adding both those ampere turns for ear gap as well as iron path. So in the series air gap, total ampere turns will be found by adding them. Okay. Same will be applicable to this one also. mmf for this ear gap plus mmf for path. This one using this formula, that will numerically be equal to this one. Okay. Done up to here. Coming upon the one another thing is there. Okay, let us erase it first. erasing this. Leakage. Let us study what is leakage. Leakage of what? Leakage of flux. Whenever there is an air gap, say this is the frame, this is the frame, the flux will be like this. The flux lines will be, magnetic flux lines will be like this. But when they will continue in between this air gap, they will bulge outwards. They will bulge outwards. Because of what? Because of the difference in permeability. Permeability of this iron part is different, and permeability of this air gap is different. So by the difference of permeability, those magnetic flux lines will bulge outwards, or magnetic flux will swell. It will swell, it will get fat. Okay, after swelling, what will happen? Some of the magnetic field lines will be lost, and that will be called as leakage. That will be called as leakage. Okay, leakage will be given by leakage factor. Leakage factor is equal to total flux upon useful flux. This implies total flux for the convenience of calculation. Total flux is referred to in the iron part itself. We say whole of the flux is confined in this iron part only. But some flux is there that connects very feeble amount of flux, because the air gap is often small. So some part of flux will be linking in between this air gap also. Okay, this flux that links the air gap, this is called useful flux. The flux of this air gap is called useful flux, and total flux is the flux in this iron part. This implies leakage factor is flux in iron part divided by flux in air gap. But air gap leads to the swelling of this flux line, magnetic flux lines. Then what happens? There is leakage. Some of the lines are lost on either sides, or in the 3D on all the sides. After swelling, some of the lines are lost, and this leads to leakage. And the leakage is given by leakage factor, which is equivalent to this formula. Leakage factor for modern electrical machinery. Modern machinery with air gaps, that is 1.2. The value for that is 1.2. This could be asked in a certain exam as well. What is the leakage factor for modern electrical machinery? That is 1.2. Okay. What is fringing? Yes, this is called as fringing. The swelling of this air gap, the swelling of this flux in the air gap, that is called fringing. And to avoid fringing, this swelling is called fringing. Swelling is called fringing. To avoid fringing, what we do? To avoid fringing, we place coil as close to air gap as could be possible. possible. So this leakage, this fringing and thus causing leakage, this is an anomaly. This is a decreased efficiency of one kind. So to avoid the decrease in efficiency, what we will do, we will place the coil as close to the air gap. There will be very less distance between the coil and the air gap. Only in that case, the leakage will be less because of less fringing. Okay. So we are acquainted with fringing, leakage factor, and air gap. Now, coming to the next portion. Okay. The next one is magnetization. Magnetization or BH curve. Directly coming over it, if we plot magnetic flux density B on the y-axis and magnetic field strength H on the x-axis, the plot will be something like this. The plot will be something like this. Let us mark certain points on this line: A, B, C, D, and then beyond D. Okay. We know the formula. B is equal to mu R, mu naught H. So this implies mu R. The relative permeability, mu naught is constant, that is fixed, 4 pi into 10 power minus 7 Henry per meter. Okay. This will be B upon mu naught H. Okay. Here, let us see. We have a certain magnetic field with strength H. The strength of magnetic field is H, which is increasing gradually. First the magnetic field is weak, feeble, then the magnetic field increases in its intensity, or the strength of the magnetic field increases, that is x-axis increases, H increases. If we place a block of iron in that magnetic field, what will happen? There will happen magnetization in the iron piece. All the small clusters in that iron piece, they will be aligned in one direction with gradual increase of H. What will that cause? The gradual alignment of those small clusters, small molecules in that iron block, the gradual alignment of those will cause B to increase, magnetic flux density to increase across that small piece of iron. That will increase the flux in that small piece of magnetization, will increase the flux density in that small piece of iron. We have already discussed it in our previous chapter. You can go over there and see the concept behind that. Okay. With increasing magnetic field strength, the material, the block of iron will be magnetized, and with the gradual magnetization, gradual alignment of the molecules, B will be increasing. But when the piece of iron that is fully magnetized, means all the molecules or clusters or whatever you call them, they are aligned in one direction, proper north and proper south pole, they are established. There will be no further magnetization. And the B will constrict itself to a fixed value. Okay. Here beyond, you are watching here B is not increasing. B is not increasing. B has come to a set value like this and set itself up to this point. But still, if we are increasing the strength of the magnetic field, magnetic field is getting stronger and stronger gradually with time. What will happen? The B has fixed its value. With the strengthening of the magnetic field, there will be no effect in B, because the material, the block of iron, is completely magnetized. Now there will not be any further magnetization of that, because all the clusters or molecules, they are aligned in one direction, completely 100%. Okay. What will be the effect of that? Mu r equal to B upon mu naught H. B will first increase and H will increase, B will increase. This will give rise to this part. And when B will be set to 1 point, say B increases, H increases, then mu r will have a certain value, changing value. Sometimes what will happen? B increases less and H is increasing at a constant rate. Okay. Here beyond B will increase less. Here B is steeply increasing, but here beyond B is increasing less. So mu r will change its values. But when B is fixed, but H is still increasing, the values of mu r will fall. Say first this the fixed value of this is 5. 5 divided by constant. Mu naught is constant. H is increasing. First of all, let it be 5. Then this will be something around 1 upon 1 divided by constant. This will give a certain value. But if H is still increasing, this will become 10. 5 upon 10. Then mu r will be decreasing. So what do we infer from here? Mu r, or relative permeability is not fixed. It is dependent upon this B. It is dependent upon this magnetic flux density B and magnetic field strength H. If we don't limit the strength of the magnetic field, then what will happen? The value of mu r will gradually decrease, because the B is fixed and this is increasing. Numerator is fixed and denominator is simply increasing. That will cause the net value of the number to decrease. So mu r has variable values at the variable instants of time, where B and H, they are either increasing steeply, they are increasing at a flat rate, or B is not at all increasing. Mu r will have different values. So what does magnetization or BH curve tell? It tells us about mu r, relative permeability, that it has different values according to B and H. Okay, thank you. We shall be studying furthermore regarding magnetism in our next lectures. Okay, thank you.